Hey there, chemistry team, chemistry coach, coming back at you again. Man, how many of these have you watched? We are ready for video number 8 in our electrochemistry journey, even though the first one technically, our first 4 are technically reviews. So if you're on top of it, you don't really need to watch those, but I highly recommend it. What else you got to do, right? Do a Netflix binge. You can Netflix binge. Well, you can't really Netflix binge this because I'm not on Netflix, but you can YouTube binge chemistry videos. Sounds like a good day. Here we go. Let's put everything together and officialize it, right? So we've been talking about cell potentials and electrode potentials and standard and non-standard conditions, all this garbage. Let's focus in on what are we going to do if we got a problem. All right. Let's look at standard cell potentials, the overall cell potential between the anode and the cathode. Anodes on the left, cathodes on the right. At standard conditions, we do not know how to calculate these at non-standard conditions yet because our defined reference point, the standard hydrogen electrode, or She, which is given a value of 0 volts, is under standard conditions only. So if we're going to use these values in our standard electrode reduction potential table, those values are standard conditions only, my friends. If you're not at standard conditions, you'll have to wait for a later video. Here we go. Same idea as thermodynamics, right? Calculate delta G naught, figure out your temperature, then calculate it at delta G at non-standard conditions using Q, all that kind of garbage. So same thing. When we do it at non-standard conditions, we'll just take it as standard conditions and add a correction factor to it. No big deal. But we got to be able to do it standard conditions first. Here we go. And this is just what I do. Go through the steps. You have to do steps 1 through 4 in my class. Step 5 is optional. So number 1, you can't do anything unless you know what your reducer and your oxidizer are. What's my reduction half reaction, right? What species is being reduced, and what's my oxidation half reaction? What species is being oxidized? The good thing about electrochemistry is these half reactions are provided for you or hinted to you. Either they are given to you directly off of this table, literally, they will be written down for you, or the overall reaction will be given to you and you have to extract from it the oxidation half reaction, the reduction half reaction, or they'll give you hints like, hey, here's hydrogen peroxide in acidic solution. Does it react with some other species in acidic solution forming this? And then you got to go, oh, crud, didn't give me the products on one of them. Which one of these is it? So you just scan through for the reactant, find the products, find the appropriate half reaction. And remember, the reduction half reaction will be written as stated because these are reduction potentials, okay? Under standard conditions. The oxidation one at the anode will be flipped. These are all for cathodes. So if you have the anode, it's going to be the same equation just backwards, which means we have to change the sign on that if you do it the way I do it. All right. So find and write down your reduction half reaction. Find and write down your oxidation half reaction with the electrons. Step 2, find them on the table, right? Find them on here. That takes the most time. You're like, where is the stupid thing? Write them down and find the standard electrode potential and write that value down next to it. If it's the cathode, the reduction one, then it is the value on there. If it's the anode one, you're reversing the equation, so you have to change the sign on it so that you can do step 4 later, right? So step 3, I want you to combine the reduction and oxidation half reactions. Make sure you balance the electrons out. If the electrons aren't the same, you got to multiply the equations to get the lowest common multiple like we did in one of the review videos of redox reactions. Give me the overall equation. I want that. Now, sometimes I'll give that to you and you have to figure out the other one. Sometimes I don't. So Merry Christmas if I give it to you. Then once you have them, just take the cathode half reaction, cell potential, the electrode potential from the table, plus the anode one, but we changed the sign on it. Because I add those, we have to take the anode half reaction, right, the oxidation half reaction, which is the reverse of what's on the table, and if we reverse an equation, you change the sign. That's why I like this one with the positive sign there, with the addition, positive sign, the addition sign. I like to add them because it forces you to think about that the anode is the reverse of what's on that table, so you have to change the sign on it. If you use the other equation where it's a subtraction, you don't do that. So yes, the math is easier, but it's easy to get confused. So I'm more of a fan on that. If you use the other way, that's fine. I'm okay with it if you do the one where it's a cathode minus the anode. You just have to keep track in your head what's going on. But I'm still going to make you write equations. I'm going to go let a cat out real quick. I'll be right back. All right, so many cats and pets. Here we go. So we've written our half reactions, found our values on the table, reversed the sign on the anode, added them together to get the overall equation, added the two electrode potentials, and that gives us our overall cell potential at standard conditions. Remember, we're stuck at standard conditions. And then step 5, you may or may not have to do. Steps 1 through 4, you have to do. Step 5, what if I ask you for the cell line notation, right? Where you're drawing the overall equation, but you're doing it with the vertical lines and the double vertical line for the salt bridge. Kind of is a different way of looking at the reaction. And I might ask you for the overall electrochemical. If I say draw the voltaic cell, draw the galvanic cell, draw the electrochemical cell, something like that, or draw the cell diagram, then you got to do the dumb beakers and the gas ports if you have a gas, the voltmeter and the salt bridge and the flow of the ions and the electrons zipping around, all that fun stuff. That's my favorite part. You just kind of go through there. Even though I'm not a great drawer, I like to draw. So, and again, watch out. Some people call, some books call the cell line notation the cell diagram, so it gets confusing. But I tend to represent the cell diagram as with the beakers and the voltmeter and all that stuff. And then the line notation is kind of a bridge between the overall reaction and the cell diagram with all the beakers and stuff. So it's kind of a halfway in between. Sometimes I'll ask for all of them. Sometimes I won't go past step 4. Sometimes I'll ask for one or the other. I like them all. Right? So let's do 2 examples on this video. I'll start with a more simplistic one. Then we'll get to a little more challenging one. Lots of, not an infinite variety of questions I could ask you, but I could do any one of these babies. Yeah, and this is not even a complete table. Yes, we could have fun with this. So get your calculator and your brain ready to go. Let's do some problems and let's go through systematically. There's a lot of information. Let's just go through these steps. And later on, when we do it at non-standard conditions, then we got to add some more steps. Oh, man, what can we do? All right, you ready for example number 1? Very much what you will probably end up seeing on a quiz and definitely the next exam. I'm guaranteed. All right, here we go. I said I'd start with a simple one, then we'll do a more complicated one. For the lead-2 ion in solution being displaced by aluminum solid, right? So we got to understand the aluminum solid is going to be donating electrons to the lead. The lead's going to plate out as solid lead, right? So the lead-2 will be reduced to solid lead. The aluminum solid will be oxidized to aluminum. You should know what charge aluminum prefers. It's a type 1 metal. I wonder what that charge is if you're not sure. So what is the overall equation? Of course, you got to do the, so I want you to pause the video and work on this. Do the reduction half reaction, the oxidation half reaction and the reduction half reaction. Add them together, right? Make sure the electrons cancel out. Find the common multiple if they're not the same. Write the reduction potential, the reduction electrode potential from the table. Write the anode oxidation potential, which is the negative of the value on that table. Calculate standard cell potential for the overall cell. Is it spontaneous? Now remember, E cells that are positive or greater than 0 are spontaneous. Anything less than 0 or negative are not spontaneous as written. I'm doing the full meal deal here, buffet. Do the cell line notation with the vertical lines, and then draw the entire electrochemical cell with all the beakers and voltmeters and salt bridges. Pause it, have at it. See how you do. And then I'll do them in sequence. Although I like to combine A and B. A, B, and C I can kind of all do together. And then D I'll do separate, and E I'll do separately. See if you can do this one. How you doing so far for part A, right? We just want the overall equation. I think everything is easier when you can see the overall equation in the 2 half reactions. If you skip it, a lot of times you'll miss stuff on the test, I guarantee you. All right, here's our reduction half reaction. The lead-2 is picking up 2 electrons to form the lead solid. Our oxidation half reaction, the aluminum solid is forming the aluminum plus 3, losing 3 electrons. So in the cell. This will be on the left-hand side, producing electrons, which goes over to the lead. The lead picks them up and plates out as solid lead. What's nice is we've got metals in both of these, so we don't need those platinum wires. We can just take aluminum, bend it over the beaker, lead, bend it over the beaker. Good thing these things are malleable, right? Let's look on our tables for the values. So since this is the reduction half reaction, it will be what you find here. And I found it down here. If you look on your table, all the way down, I'm looking in a mirror image here. Do you see the lead? All right, so there's lead plus 2 aqueous, plus 2 electrons going to lead solid. If you go across, it's negative 0.125 volts. So compared to the standard hydrogen electrode, that wouldn't actually go, right? If you paired that up, if you put the standard hydrogen electrode as the anode and lead as the cathode, this wouldn't happen, right? It's not going to happen because of the negative sign. If it's positive, it would. All the positive ones would react. The negative ones wouldn't if it paired up with a standard hydrogen electrode, which we don't do very often. So anyway, that's why I have the negative 0.125 volts. And very commonly, they're to 3 decimal places, like I did with my voltmeter. Now let's look for the aluminum one, but see, we're not going to find it. This is an oxidation. On the table, it'll be backwards. It'll be the aluminum plus 3 electrons going to that. So it's flipped. It's reversed. Okay? And I didn't find it on the front page anywhere. I found it on the back page. Oh! Right? So I found I don't know if you can see it right here. See the aluminum plus 3 electrons going to aluminum solid? That's backwards of that, right? Because this is as an oxidation, as an anode. This is as a reduction, as a cathode, because that's why it's a reduction half cell potentials. All right, so, I lost my aluminum. There it is. So I need to reverse this reaction, which means I need to reverse that sign. So you see the negative 1.676 volts? That's what it is as a reduction. So I have the negative 1.676 volts from the table, but I'm going to put a negative sign on it because it's reversed, right? So this is reversed from the table. You don't have to write this down. You never have to write that down, but that's why I put that negative sign there. If you use the equation I do, where the overall cell potential is the anode, the cathode, plus the anode, you have to put that negative sign there, which makes sense because this is backwards from what's in the table. So the cell, the electrode potential should be the negative of what's on the table. It just makes more sense to me that way. But I'm finding fewer and fewer people do it because they skip all this stuff. And I think a lot of students get by electrochemistry not really grasping what's going on. Yeah, you can put the 2 values in there, but do you really know what's happening? This proves to me you know what you're doing. So the actual anode electrode potential is positive 1.676 volts, the reverse of what's on there. Let's add these 2 equations together to get the overall. Notice, do you see? Can you see what I see? The electrons, if I add these together, those electrons aren't going to cancel out, are they? 2 and 3. So what's the common multiple between 2 and 3, my friends? 942. No, 3 factorial. All right, so we got 6. So I have to multiply this by 2, and I have to multiply this by 3. So we'll end up with 6 electrons on the left and 6 electrons on the right. Now, I'm not going to do the overall. Hopefully, you can see that those will cancel out in the process. So the overall equation, which is what was asked for in part A, correct? I'm going to have 3 times 1, or 3 of the lead 2 ions, right? Plus 6 electrons, which are going to cancel out. And then over here, I have 2 times 1, or 2 aluminum solids. Technically, these are reversible. Right? A lot of times we don't write the reversible, but these technically have reversible arrows on them. That's everything on the left. Over here, we're going to get 3 times 1 is 3 of my solid lead. I'm going to get 2 times 1, or 2 aluminum plus 3 ions. And then the 6 electrons, right? 2 times 3, 6 cancels out. And that right there is why I put the review videos from redox, because you got to be able to add those half reactions together and cancel out those electrons. Now for part B, it's really easy to get the overall cell potential. All right. So that's just going to be the cathode plus the anode. So you don't even need the equation if you add them. The other way you have to go, God, what do you subtract from what? This one, it doesn't matter. You can do cathode plus anode plus cathode. It's irrelevant. And we could just add the negative 0.125 volts plus the positive 1.676 volts. And we got it. Both good to 3 decimal places. And if the overall cell potential is positive, that'll be spontaneous at standard conditions. If it's negative, it'll be non-spontaneous at standard conditions. Easy peasy. So this would be negative 0.125 volts plus 1.676 volts. 3 decimals, we're limited by decimal places. The math in electrochemistry is actually quite simple at this point. But I guarantee you, no matter what we're doing, how complicated, you're going to need this. You're going to need the overall cell potential at standard conditions. And then we can adjust it if we're not at standard conditions. But you're always going to have to do this. Always, always. And you need this equation here to figure out the parts C and D that we're going to be doing. All right, add these together. Let's see what we get. We get 1.55. That's going to go down. So is that positive 1.551 volts? Boom. And since that's greater than 0, we can do part C. E naught cell greater than 0. So this is spontaneous as written. Okay, I'm going to go a lot faster on the second example we're going to do. All right, that's spontaneous as written. So do the cell line notation for me and draw the cell diagram. Have at it. All right, let's walk through the cell line notation. You ready? Anodes on the left, cathodes on the right. Correct? So the anode was the oxidation. That was the aluminum, right? So we've got aluminum solid. That's going to be our electrode. We need a vertical line between that and the solution because that represents 2 different phases, correct? And since we're at standard conditions, we can write 1 molar, or you could do activity equals 1. I take both. Then we're going to have the salt bridge that separates them, so get the 2 vertical lines. Then we do the cathode half reaction, right? So this is the anode. And the cathode is the lead-2 ion reducing to the lead solid. So we're going to have the lead-2 ion at standard conditions. So you could write 1 molar or activity equals 1. I need a vertical line to separate the solution from the solid electrode. We got the liquid and the solid phases. We don't need any platinum, right? Because these are actual metals. So that's your cell line notation. Anode. Cathode half cell, right? You don't have to write the anode cathode. You just got to put it in that order. So now from this, we could draw the cell diagram. So pause this, draw the electrochemical cell. I'll erase anode cathode, but I'll leave that up on top there, and I'll put the cell here. It's going to take me a little bit, so I'm going to pause it and draw it. Let's see if yours looks like mine. Let's see how your picture, hopefully it looks better than mine, if you guys can draw better. Some of you are just amazingly fantastic at drawing. All right, so here's the cell line notation. Here's the electrochemical cell. And this will be a galvanic or voltaic cell because it's spontaneous. If it wasn't spontaneous, if that was negative, that would be an electrolytic cell we'll look at in a different video. All right, I got my anode over here. I got my solid aluminum bent over a beaker inside a solution of aluminum, probably like aluminum nitrate or something like that, +3. The anode is negative. That's where the electrons are being generated. So sometimes it's good to put the terminals. Sometimes you actually see that on the voltmeter. You see a little negative here, positive here. So this would be the black lead from your voltmeter. This would be the red lead to the cathode, which is positive. So over here, I've got the solid lead bent over the side of the beaker for the cathode electrode, which would be positive. Inside a lead-2 solution, probably lead-2 nitrate, lead-2 sulfate, something like that. So for the reaction, the aluminum is becoming aluminum +3. So I got the arrow pointing from the solid aluminum to the aluminum +3. generates electrons. Always draw the direction of electron flow. Since it's spontaneous, it goes anode to cathode. If it was negative, the electrons would flow the other way spontaneously, right? We got the 1.551 volts there. Ha! We know what that value is. That's what we'd read on our voltmeter in lab if we did it right. Like if we had bubbles in our salt bridge or something, or we had gunk building up on the electrodes, it might, lower it a little bit. We've got the salt bridge here. If you can draw clamps better, if you can draw alligator clamps better than I can, great. You don't have to. You just have them touch the electrodes. As long as they're in contact, electrons can flow. But remember, without that salt bridge, that on-off switch, this ain't going to happen. So when that salt bridge goes in, it's filled with some kind of salt, non-reactive salt solution, almost always potassium nitrate, with the little cotton or porous plugs here. So as the aluminum ions build up, it becomes 2 positive at the anode. So for every aluminum 3 nitrates come over. Over here, for every lead 2 that you lose, 2 potassiums come in. One way to think about that is the anion flows to the anode, and the cation flows to the cathode. Cathode, cation, anode, anion. So anions go. I like to think of it because, that's becoming too positive, so the anions go that way. That's becoming less positive, so the positive ions go that way. I like to think of it, but if you get confused, anions go to the anode, cations go to the cathode. Boom! Let's do a harder one and see how you do, but we're going to do it faster. All right, problem number 2. Ni ichi ni sanshi ichiban. All right, I don't know what I was just screaming there. Can the permanganate ion in aqueous solution oxidize hydrogen peroxide into oxygen gas, diatomic oxygen gas, in acidic solution? That makes a big difference. Forming the manganese 2 ion. And so since I didn't give you the half reactions, I had to specify, because if you look on here, the permanganate ion, you've got one forming MnO2 here, you've got one forming Mn2 plus there, so that's the one we're interested in, MnO4 minus forming Mn2. I think I saw it a few other times down here as well. I think there's like 3, maybe 4 times you run into the permanganate ion. So if I didn't tell you what it formed, you wouldn't know which half reaction to use. So you just cruise through, find the MnO4 minus forming Mn2 plus, because that's reducing. Then the hydrogen peroxide is going to be oxidized, so you got to find the one with H2O2 forming O2 gas, but it's going to be backwards from here because that would be the oxidation. These are all reduction. See if you can find those two. Write the reduction and oxidation half reactions. Find the electrode potentials. Remember to put a negative sign in front of the anode one. Add them together and see if you get a positive value or negative value. Positive, yes, it'd be spontaneous and this would happen. Negative, no, it'd be non-spontaneous. It wouldn't happen. Give it a shot. Of course, we're going to draw overall reactions and cell line notation and draw all our beakers and voltmeters. Go for it. All right, that's all I could fit on my first board. This is quite a bit more challenging than the other one. All right, we've got a reduction half reaction. We found that. We found the MnO4 minus plus 8H plus 5E minus going to Mn2 plus 4H2O. That has a value of positive 1.51 volts. Can you see that? It has the positive 1.51 volts. That's why I have this equation here with the 1.51 volts, and that's as written as a cathode. Now the anode, we have to find this, so we've got to look for it. Where is that at here? I'm going to pause this and find it. I can't read very well. I'll find it. Hold on. There it is. I don't have my old man glasses on. These are so small. So here's O2 gas plus 2H plus, giving 2E minuses plus H2O2. Remember, what we're looking for is the H2O2 forming O2 gas. So we've got the anode, which is backwards from here. So we're doing H2O2, giving us 2 electrons plus 2H plus 2 oxygen gas. That's what was stated in the problem, right? H2O2 forming O2 gas. H2O2 forming O2 gas. This equation is here, but it's backwards. Right? It is backwards because it's the anode. Okay, do you see the 0.695 there? So that, as an anode, if we reverse it, it's going to be negative 0.695. So I put the negative in front of the 0.695. So as an anode, as an oxidation half reaction, this is negative 0.695 volts, right? Because we got it flipped. So then we just add those together. Haven't got to that yet. Notice we got 5 electrons here in the reduction half reaction and 2 there. We need a common multiple of 10. So I need to multiply the entire reduction half reaction by 2, the entire oxidation half reaction by 5. So if I multiply by 2 and 5 there and 5 there, this will be my overall equation. So I get 2 permanganates, 16H plus, 10 electrons, and then 5 H2O2. And then over here I'm going to get 2 Mn2 plus, 2 times 4 is 8 waters, 5 times 1 is 5 oxygens, 5 times 2 is 10 hydrogen ions, and 5 times 2 is 10 electrons. Do you see the 10 electrons canceling out? Subtract 10H plus from both sides, that goes away. That goes to 6. So on the next board, write the overall simplified one, put the states back in, and calculate E0 cell for me. All right, this is a lot harder than the other one. You ready? So add the 2 together, right? You cancel out the electrons, reduce the H plus, all that fun stuff. So you end up with 2 permanganates plus 6 hydrogen ions plus 5 hydrogen peroxides, giving you 2 manganese, 2 ions, 5 oxygens, and 8 waters. That's the overall equation going on. So let's take the cathode, which is straight off the table, 1.51 volts, add the anion electrode potential, right, which is the oxidation part, which is the reverse of what was on the table. We flip the reaction over, negative 0.695. So we end up with 0.8150 volts, rounds to 0.82 volts. That is greater than 0. That is spontaneous. So yes, the permanganate ion can oxidize hydrogen peroxide to oxygen gas, leaving you Mn2 plus. That can happen. So if we do the cell line notation, this is a whacker-do. Look at the half reactions, right? You can't really tell it from the overall. I wish I had space on my board. If you look at the half reactions, the anode goes on the left. So the hydrogen peroxide, since there's no metals there, we need platinum to do it. So we'll have a platinum electrode. Hydrogen peroxide is oxidizing to O2 gas, so we need a vertical line in between the phases there. We got a solution and a gas there. And you get the H plus as well, so we got the line there. Then we got the salt bridge, and then the cathode, the reduction half reaction on the other side. In that one, the permanganate ion with the H plus, so I have a comma between those, they're the same phase, produces Mn2 plus, comma, because they're the same phase. But there's no metals in there, so I need platinum solid for an electrode, so I need a vertical line to separate the solid platinum from all the species in solution. Remember, anode half reaction, the oxidation half reactions on the left-hand side of the salt bridge, the cathode or reduction half reaction on the right-hand side of the salt bridge. Separate different phases with a vertical line. So let's draw the cell diagram. We're done. Go for it. Draw your beakers. This one took me a while. All right, you ready? Got my 2 beakers, got my voltmeter with my thing. Yeah, you could have gone 0.82 there. If you had a crappier voltmeter to 2 decimal places, maybe put on the wrong reading. So I've got my platinum wire here with my platinum plate inside an oxygen tube, so oxygen gas can go in or come out. The hydrogen peroxide, this is the anode, right? Which is going to be negative. The hydrogen peroxide comes over here. It's going to strike the platinum, right? It's going to produce oxygen gas and hydrogen ions. Right? So that reaction is occurring on the surface of that platinum. Electrons are generated at the anode, travel through the voltmeter over to the platinum. And instead of a platinum wire, I thought I'd just use a big platinum, huge platinum piece, even though that's probably worth $1,000 and would disappear in my pocket. So I've got the platinum here. The electrons build up on the cathode. The permanganate ions, hydrogen ions, strike that, pick up electrons, forming the Mn2 plus in solution. Of course, potassium ions, the cations, flow towards the cathode from the salt bridge. The anions flow towards the anode in the salt bridge there. Cathode's positive, anode's negative. Electron flow, ion flow. These reactions were a lot tougher. That's as hard as you can get. If you can get that, you're good to go. So next video, we're going to get into things like non-standard conditions, right? Because I didn't write any values here. I didn't have room, but these are all 1 molar, activity of 1. The pressure is 1 bar. I just ran out of room. And then we're going to also relate this to some thermodynamics and some equilibrium. Oh, they're all going to come together. Come together.